Let's bring up the demonstration. Starting with the first section, Symbol Builder. I will first widen the screen, and then I will move to the integrated PDF extraction. Starting with the integrated PDF extraction, I will bring up a catalog of parts. In this particular case, we will model a complex circular connector part to be used in the schematic design. Bringing up the catalog of circular connectors, I will page through the connectors, and you'll notice that the pin locations are defined in the datasheet and are also defined in the PDF tables within the datasheet. We'll be modeling this 37-pin connector part to start with. Using the integrated PDF extraction, let's create a PDF template or table. I will select the green button to complete the table. And then I will use the tag buttons to tag or ignore rows that I do not wish to transfer, tagging the individual rows not to be transferred to the Scratchpad spreadsheet. The last step is to transfer the content to the Scratchpad. Let's go and complete the second section of the table. Extracting the content from the second table, completing the table, and tagging the content which I wish to ignore. In this manner, we can extract very, very complex tables from the PDF in a fraction of the time, supporting both read and read-only PDF formats. Let's move to the Scratchpad spreadsheet where we transfer the content. And you'll notice that the raw columnar content has now been transferred to the spreadsheet. The first step is to give the columns very specific meaning, including number, X origin, Y origin. And then I will scale the units, in this particular case, from inches using the scale units command to the particular units that I will be modeling the part in this case, millimeters. Once the scaling is complete, I can then transfer the content to the main spreadsheet using the copy tag content, which I will later use to model the schematic symbol model. And I will also use this data sheet to model the PCB footprint. Using the configurator, let's configure from the symbol builder portion of the product to the footprint builder. In the footprint builder, we have a host of calculator types, including caps, BGAs, CGAs, chip array, CQFP, crystals, diodes, LCCs, LGAs, molded, oscillators, PLCCs, QFNs, Ps, SODs, SOICs, Js, Ns, and Ps, SOTs, and TOs, and plus the through hole and the connector calculators, including DB, right angle, DTL, shrouded headers, and a host of calculator types coming online. Bringing up the circular connector, you'll notice the pins are off to the side. The Preferences tab contains the specific information. The Layers tab, the layer information, and the Component tab contains all of the dimensioning information, plus the pad stack tabs to select different pad stacks and drafting tabs for user-specific line widths, silk screens, assemblies, and other constraints. Let's go back to the symbol builder, integrated right directly into the product. And under Update, we will now annotate the PDF datasheet extraction to the footprint model. Completing the annotation, we will configure back the footprint builder. And notice that the pins have been moved to the XY coordinate for the datasheet. I have completed the part. I'm now ready to export this to my specific EDA tooling systems, Allegro or PADS layout. Selecting Allegro, I will export the part to Allegro, first saving the library in my library of parts, and then invoking Allegro immediately invokes Allegro and moves the content directly into the Allegro system. I now have completed the part directly to Allegro. Let's take down the Allegro tab, and the next step will be to model the symbol model. Selecting the configurator, I will move back to the symbol builder. In the Scratchpad spreadsheet, which we transferred to the main spreadsheet, we have the pin number, which I will copy the column into the pin name column. A lot of users then apply a character in the front, for example, P. And using the intelligent editor, we will append to the front a P so that the pin names begin with P and then the individual number. Checking the data sheet, I now have 37 pins. I will now move to the partitioning of the symbol set, creating the schematic symbol model. Selecting the Symbol Partitioner tab, I will change the width to 6 units from the standard default 20. I will select a group of pins. The pins I will select from the Symbol Partitioner. And it's very important to note that at this point, all control is under the symbol planner. If you have 37 pins, you will end up with 37 pins. They exist somewhere on the floor plan or on a schematic symbol model. Using typical editors, sometimes users will drop pins in the middle. That is not possible with the partitioning manager that manages all of the pins once the symbol set has been checked. You can see how easily I have moved the pins and supporting different styles, for example, corporate styles for individual corporate, or switching the style to ORCAD capture in this particular case with a 3-pin whisker length. I will now save the part and also attach the footprint model directly to the schematic symbol model. And you'll notice the PCB footprint land pattern name at the lower section of the display. Creating the relationship between the symbol model and the footprint model. Bringing up both tabs or both windows, I have complete integration and control to ensure that the symbol model matches the footprint. I can cross-probe. I can obtain reports. And I can identify very specific pins or groups of pins, such as an FPGA, the banks, or the I/O standards. Let's move to the next step. I will now export the completed model to ORCAD capture. But we support a host of exports, including ORCAD, Allegro DE-HDL, DX Designer, PADS Logic, and others. Let's invoke OrCAD Capture. We will import the model directly into OrCAD Capture. I will now open up the library, the OLB file, and view the part, completed part with its integration to the PCB footprint land pattern model with the pack type modeling. Taking down the PCB footprint land pattern model and the schematic symbol, we will now save the part. But before saving the part, let's show some of the other capability. For example, if I grab these group of pins and move the pins from the left side, dropping them on the right side, it pushes down all the remaining pins. Let's go back to the Scratchpad spreadsheet and demonstrate some of the other capability. I'm going to reset the Scratchpad, and I will import from a CSV tab separated value file or a PDF file the actual signal net names applied to this connector. You'll see the actual signal net names which go off through the harness. And if we want to add more intelligent information, we can add it, such as the signal net names, the direction codes for modeling, to other downstream tools, and we can annotate that information from the Scratchpad spreadsheet to the symbol model. Going back to the main spreadsheet, you will now see the signal names, and if I had direction codes, they would be annotated. I will widen the width out to 14 units, and I now can view the annotated information from the spreadsheet to the symbol model. I can export the symbol model with the pin numbers, or I can export them with the actual signal net names, giving the symbol model much more intelligence for those users which want to use customized symbol parts. Let's complete the process here by saving this individual part, and what I will do is close and save all of my parts and restart the EDABuilder, bringing up the second part which I wish to model. Let's bring up the PDF datasheet for the second part. In this case, I will be modeling a standard integrated circuit, a Cypress part. We can import a diagram, such as these flat pack diagrams or a BGA map. Or in this case, I will import a PDF template in a matter of seconds. Completing the PDF, I will now tag the column rows to be ignored on transfer. And I will transfer the content to the Scratchpad spreadsheet. Moving to the Scratchpad spreadsheet, you'll see some cells, like for example, reset and service in red. Those are cells which have overbars in the original PDF content. Let's append an _L indicating negation to those specific cells. I will now tag the individual columns, in this case, pin name, pin direction, and pin number. In the previous case, where we were modeling the PCB footprint, we had X origin and Y origin. Let's take the table now and copy the content to the main spreadsheet. Bringing up the main spreadsheet, I now have the pin numbers, pin names, and pin directions. Let's check the data sheet, and I have one warning, an invalid pin direction code. And you'll notice, if we go back to the original PDF data sheet, that communication network interface is actually in the data sheet, in the pin direction column. You'll also notice that VDD and VSS model in the data sheet is defined as inputs. We will correct those now at this time. So let's change the pin direction to input. And using the intelligent editor that understands the content in each individual column, all I do is click on the column and it'll provide me the available options. I've now tagged the VDD and VSS, checking the data sheet. For some EDA tools, they require unique pin names. We can automate those using the automation function. But first, let's talk about some of the additional capability. For complex microprocessor data sheets, special handling of syntax, such as in the Freescale data sheets with multifunction pins. In this case, I will automate the clocks detection and in negated logic. And you'll notice when I invoke the function that I automatically detect my clock pins. I can also create the unique pin names at this point, with VDD, VSS, and NC appending a pin number or a sequence number. The next step will be to check the data sheet, and I will perform, in this case, an automatic assignment of the pins to the symbol set, with maximum pins on the side is set at 80, and the assignment of the power and ground to the last fracture. We support both automatic generation of symbols and interactive, which we will be demonstrating in a second. Bringing up the first symbol, you'll notice the intelligent placement, individual groups of pins sequenced together as a bus with a spacer between the two. If I do not like the order, for example, high to low or low to high, I can resort the data sheet and then replace the pins after the specific sorting. Let's go back now to the automation and replace automatically the complete symbol set with 80 pins on the side and assigning the power ground to the last fracture. And you'll notice after sorting, we now have busing high to low. We also support the interactive assignment, which we will be demonstrating next. Let's move back to the assignment and unassign the symbol set pins, and we will use the interactive placement to interactively place the pins in the exact XY position. Moving to the symbol partitioner, I just simply click on select and drop, and then I drop the pins from the spreadsheet to the symbol model. Taking the CP bus and putting the input on the left. The data bus from D7 to D0, and I will place that on the right. The I/O bus. So you can see how quickly we can make an assignment of a fractured symbol set in a fraction of the time. Making the assignments of the output pins, as I place them on the top, it pushes everything down. And notice that my clock has a proper clock indicator and my negated pins with the negation code. Moving to the second symbol, I will move the VDD to one side, the VSS to the other side, and I will place the NC on the top. I can move pins between symbols, back to the floor plan, and to the symbols, all under the control of the symbol planner.